For years, the search for the solar system's missing giant, the so-called Planet 9, has been framed as a story about gravity, a celestial detective story written in the language of orbits and perturbations. But it's not. At its heart, this is a story about darkness. This is the James Webb Space Telescope's first deep-field image. It's an astonishing porthole into the infant universe. The patch of sky it represents is no bigger than a single grain of sand, held at arm's length against the night. Yet within that infinitesimal window, we see not emptiness, but thousands upon thousands of galaxies. Some are so ancient, so far away, that their light began its colossal journey to us over 13 billion years ago, when the cosmos itself was just a toddler. We have engineered a tool that can see to the very edge of time, capturing the ghosts of the universe's first dawn. And yet, despite this almost godlike power, we are profoundly, deeply, and almost completely blind in our own cosmic backyard. The most profound mysteries, it seems, are not always the most distant. The math, the compelling, undeniable, and elegant physics of gravity suggests that a giant planet, a world perhaps 5 to 10 times the mass of the Earth, could be out there, silently orbiting in the deep dark. The evidence is written in the strange clustered orbits of a handful of tiny, icy objects in the far-flung reaches of our solar system. Their paths through space just don't make much sense without some massive, unseen object gravitationally herding them. But so far, every single search has come up empty. Not because our telescopes are weak, and not because the math is necessarily wrong. Every search has failed because a brutal, unforgiving, and fundamental law of physics might be deliberately hiding this world from us. In this video, we'll explore that law, the one that makes seeing into the vast darkness of our own solar system so incredibly difficult. We will unpack why the very same mathematics that points to Planet 9's existence is the same math that explains why we may have never, ever found it. It is a cosmic paradox, a battle between two pillars of physics, with a missing world as the prize. The story of Planet 9 begins not with a telescopic picture, but with intricate calculations on paper and the slow churning of computer simulations. In 2016, astronomers Konstantin Batygin and Mike Brown at Caltech were looking at a collection of the most distant objects ever discovered in our solar system. These bodies, called extreme trans-Neptunian objects, or ETNOs, are lonely remnants from the formation of the solar system, orbiting far beyond even Neptune. As Batygin and Brown mapped their orbits, they noticed something bizarre and utterly unexpected. Instead of being scattered randomly across the sky, as you'd expect from a collection of unrelated objects, their orbits appeared to be startlingly aligned. Imagine throwing a handful of sticks into a river. You would expect them to float downstream in a chaotic, jumbled mess. But what they saw was the equivalent of all those sticks pointing in the same direction, tilted at the same angle. It was as if these tiny frozen worlds were being herded by an unseen gravitational shepherd. A massive ghost in the cosmic machine whose immense gravity was corralling them into a bizarrely orderly pattern from an impossible distance. The odds of this being a simple coincidence, they calculated, were vanishingly small, something like 0.2%. The most tantalizing and logical explanation was a massive object, a ghost planet, shaping these orbits from afar. Now, humanity has played this game before. This is almost exactly how we discovered the planet Neptune in 1846. Astronomers in the 19th century noticed that Uranus was wobbling in its orbit. It wasn't quite where Isaac Newton's laws of gravity predicted it should be. The French astronomer Urbain Le Verrier did the math, proposed that the wobble was caused by the gravitational tug of an unseen, more distant planet, and told astronomers exactly where to point their telescopes. They looked, and there it was, a triumph of predictive science. But Planet 9 isn't an exact repeat of that story. The evidence this time is far murkier, far more subtle. It's based on the faint whispers from just a handful of tiny, incredibly dim objects billions of miles away. And many brilliant astronomers argue the clustering could be a complete mirage, an illusion created by what's known as observational bias. In simple terms, we can't look at the whole sky at once. We point our powerful telescopes at small, specific patches, often in directions away from the dense, star-filled plain of the Milky Way. The argument is that, of course, the things we find appear grouped together because we've only been looking in a few specific places where it's easiest to see them. It's like looking for car keys only under the streetlights and concluding that all lost keys must lie in well-lit areas. The gravitational whispers are there, tantalizingly persistent, but this time, when we look where the math tells us to look, we see nothing but crushing, absolute darkness. This failure to find anything leads to a confusing and profound paradox. In the last few decades, astronomers have become unbelievably successful at finding planets. We have discovered over 6,000 confirmed planets orbiting other stars, and that number climbs every single month. Some of these exoplanets are hundreds, even thousands of light years away, so far that their light takes millennia to reach us. So why on earth can't we find a potential giant, a super-Earth, in our own solar system, practically on our cosmic doorstep? The answer, as frustrating as it is that we don't actually see most of those exoplanets directly. Finding an exoplanet isn't like taking a portrait photo. Instead, we find them using several clever indirect tricks, but the most successful by far is called the transit method. Think of a powerful stadium floodlight a mile away. You can't possibly see a tiny gnat buzzing around the light bulb itself. It's far too small and emits no light of its own. But if that gnat happens to fly directly in front of the bulb from your perspective, you would notice the brilliant light flicker and dim for a split second. That's the transit method in a nutshell. We stare relentlessly at distant stars, our cosmic floodlights, and wait for a tiny, periodic dip in their brightness. That dip is the shadow of a planet passing in front of its star. We detect the planet not by any light it gives off, but by the light it blocks. It's an incredibly effective method that has been responsible for the vast majority of all exoplanet discoveries because it uses the immense, brilliant light of the star itself as a massive backlight. But for Planet 9, there is no backlight. It is never going to pass in front of the Sun from our vantage point on Earth. It's a lonely wanderer in the perpetual twilight of the outer solar system, hundreds of times farther from the Sun than we are. We can't look for its shadow. We have to look for the planet itself. And that means we have to rely on the faintest possible signal imaginable. A few stray photons of sunlight that have made an unbelievable journey, bounced off its surface, and somehow made it all the way back to us. This is where the hunt for Planet 9 stops being a matter of cleverness and becomes a brutal, head-on battle against a fundamental law of physics. You already know this intuitively. The farther away you are from a light source, the dimmer it gets. Physics formalizes this simple observation with a rule called the inverse square law. It states that the intensity of light drops off not in proportion to distance, but with the square of the distance. Imagine you're standing 1 foot away from a candle. Now move to be 2 feet away. You aren't receiving half as much light. You're receiving only 1/4 of it. Move to be 10 feet away, and you get 1/100th of the light. It's like spreading the same amount of butter over a piece of toast that suddenly got 4 times or 100 times bigger. The light doesn't just fade. It rapidly and catastrophically dilutes into the vastness of space. But for a cold, distant object like Planet 9, the situation is unimaginably worse. This is the absolute crux of the problem. We aren't detecting light from Planet 9. It generates none of its own. We are waiting for sunlight to travel all the way out to its distant, lonely orbit, reflect off its surface, and then travel all the way back to our telescopes on Earth. This means the precious, faint light gets hit by the debilitating inverse square law twice. First, the sunlight traveling from the Sun is already incredibly weak by the time it reaches Planet 9's predicted orbit, which might be hundreds of times farther from the Sun than Earth is. Then, that pathetic little handful of photons has to reflect off the planet's surface, and we have no idea how reflective that surface is. It might be a bright, icy world that reflects a good portion of the light that hits it. Or it could be covered in dark, organic compounds, making it as dark as asphalt or coal. Finally, that impossibly faint, reflected signal begins its long, lonely journey back across the solar system to us, getting diluted and weakened again by the inverse square law. This devastating double penalty is what physicists call the 1/r⁴ problem. The brightness of a distant, reflective body in our own solar system falls off with the 4th power of its distance. Let's put that into brutal perspective. If Planet 9 is, say, 20 times farther away than Neptune, a simple calculation shows it wouldn't just be 400 times dimmer, 20 squared. It would be at least 20 to the 4th power, 160,000 times dimmer. This is why its estimated brightness is somewhere around an apparent magnitude of +22 or +23. That number is millions of times fainter than Pluto, and over 6 million times fainter than the faintest star you can see with your naked eye on a perfectly dark night. It's like trying to spot a single, non-glowing piece of charcoal from 100 miles away, using only the light from a lone candle that is also 100 miles away. This is the brutal, tyrannical law of physics that turns our own solar system into an impossibly dark and hidden place. Even if we were to build a telescope somehow sensitive enough to spot something that mind-bogglingly faint, there's another, equally daunting problem. Where in the heavens do we even look? The predicted orbit for Planet 9 is absolutely enormous, a vast, looping ellipse that may take anywhere from 10,000 to 20,000 years to circle the Sun just once. Its exact position at this very moment is a giant colossal question mark, spread across a huge swath of the night sky. This is where the design of our most powerful telescopes works against us. Instruments like the Hubble and James Webb space telescopes are built for depth, not breadth. They are designed to see incredibly faint things by staring, unblinking, at one tiny, minuscule patch of the sky for a very long time, sometimes for days on end. Their field of view is infinitesimal. It's like trying to survey the entire night sky by looking at it through a drinking straw. Searching for Planet 9 with them would be like trying to find one specific dark-colored fish in the entire Pacific Ocean by scooping out water one thimbleful at a time. It is simply not a practical or feasible way to conduct the search. This reveals another layer of bias in our astronomical searches. We find thousands of exoplanets because we know exactly where to point our telescopes, at stars, waiting for them to transit. For Planet 9, we have to do the complete opposite. We must systematically scan vast, seemingly empty regions of our own solar system over and over again, hoping against hope to catch a single faint flicker of movement. And that leads to the final, soul-crushing hurdle. To prove that a dot of light is a new planet in our solar system, you can't just take one picture. A single image tells you nothing. You have to take multiple images of the same patch of sky over weeks, months, or even years. Only then can you detect its slow, almost imperceptible crawl against the fixed backdrop of distant, unmoving stars. Confirming an object as distant and slow-moving as Planet 9 could take years of dedicated follow-up observations just to be sure it's not a statistical fluke or an artifact. It is a problem that requires both extreme sensitivity and an almost superhuman level of patience. For years, the search has been defined by frustration and dead ends. The lack of a discovery has led some astronomers to propose compelling alternative theories. Perhaps the clustered orbits are indeed just an illusion of observational bias that will disappear as we survey more of the sky. Or, more exotically, perhaps the gravitational effect is real, but it's not from a single large planet. It could be the result of the combined collective gravity of a massive, undiscovered disk of thousands of smaller icy bodies, all pulling on the ETNOs in concert. A historical cautionary tale also looms large. In the 19th century, astronomers confidently proposed a planet named Vulcan orbiting between Mercury and the Sun to explain tiny, persistent wobbles in Mercury's orbit. Searches were mounted, and some observers even claimed to have seen it. But the planet was never found. The anomaly in Mercury's orbit was eventually and perfectly explained by a revolutionary new idea: Albert Einstein's theory of general relativity, which showed that the Sun's massive gravity was warping space-time itself. The math pointed to something being there, but the conclusion, a new planet, was wrong. Could Planet 9 be a modern-day Vulcan? A ghost that exists only in our elegant calculations, but not in physical reality? Perhaps. But a new hero is now entering the fight, a machine seemingly built for this exact problem. High in the desolate, clear air of the Chilean mountains, the Vera Rubin Observatory is being brought online. It's not a drinking straw. It's a gigantic, wide-angle lens. At its heart is the largest digital camera ever constructed for astronomy, with a staggering 3,200 megapixels, ready to be mounted on a telescope designed for speed and breadth. Over the next 10 years, Rubin will systematically scan the entire southern sky, not just once, but every few nights. Instead of taking long, deep portraits of tiny sky patches, its mission is to create the greatest cosmic movie of all time, officially called the Legacy Survey of Space and Time, LSST. Its sole purpose is to map everything that moves, changes, or flashes in the night. By systematically and repeatedly sweeping the vast, dark regions where Planet 9 is predicted to be hiding, it is perfectly and uniquely designed to connect the dots of a faint, slow-moving object against the background stars. While Rubin can't prove a negative, it can't prove Planet 9 isn't there. Its data should give us our best answer yet. Within just a few years of full operation, it will either spot the faint, lonely point of light that finally reveals our solar system's missing giant, or it will show that the area is empty, forcing scientists to confront the fascinating possibility that the gravitational anomalies in the outer solar system have another, perhaps even stranger, explanation. The long, frustrating hunt for Planet 9 has forced us to confront a humbling and counterintuitive truth. It is not the immense distance that makes space so hard to explore. It is the overwhelming, all-consuming darkness. Our own cosmic backyard, the region just beyond the familiar planets, remains one of the most mysterious and profoundly uncharted places we know. The math, drawn from the elegant and time-tested laws of gravity, strongly suggests a new world is out there. A silent, frozen giant, shaping the very architecture of our solar system from the shadows. But the fundamental physics of light, with its brutal, unforgiving arithmetic, declares that this same world should be almost perfectly hidden from our view. For now, Planet 9 remains a tantalizing conflict between two pillars of physics, a ghost in the machine, a whisper in the data. The ultimate question is, will our technology in the form of the Vera Rubin Observatory finally be powerful enough to conquer the darkness? Or will this world remain a phantom forever, its presence known only by the faintest of gravitational hints? The next few years might just give us the answer, and in doing so, rewrite the map of our home in the cosmos. As the Vera Rubin Observatory begins its historic survey of the southern sky, the hunt for Planet 9 is more active and more exciting than ever. We are on the cusp of a potential discovery that could change our understanding of the solar system. To follow this incredible scientific mystery and get updates as the data starts to pour in, make sure to subscribe and turn on notifications. The answer is coming, one way or another, and you won't want to miss it.